Okay, so the first thing we're going to talk about today is going to be Pascal's triangle. Let's try that again. Pascal's triangle, which will help us for when we move on to the binomial theorem. So Pascal's triangle, this will help us with the pattern of expanded brackets. So if we think about the general pattern, okay, so this is the pattern for expanding powers of brackets. Okay, of the form x plus y to the power n directly, okay? Okay, so this would be what the pattern would look like for the expanded brackets when the power of n is different. Okay, so if we take when n equals 0, which means I've got x plus y to the power 0, then we know that just gives out a 1. Yeah, because anything to the power 0 is 1. So we will record this as just 1. Okay, and you may think that's a pointless statement, but you'll see why in a second why I wrote that. Okay, if I then go to when n is now 1, then I'm going to have x plus y to the power 1, which gives me x plus y. Okay, and what we'll do is we will record this as, and what I'm doing here is I'm looking at the coefficients attached to the algebra, the actual algebraic terms here. Okay, so I've got 1x and I've got 1y. Okay, so I've got 1 and 1. Okay, n equals 2, so I'm going to have x plus y all squared. That would give me x squared plus 2xy plus y squared, if I multiplied that out. And if we record that, so again, look at the coefficients in front of the terms. I've got 1x squared, so 1 first of all, plus 2xy, so I'm going to have 2 there, and 1 there. Okay, so I'm just writing down the coefficients. And if we go for when n equals 3, so I would have 3 brackets to multiply out, and what eventually would happen is once you multiplied all that out, you would have got x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, and again, if we record that, coefficients would be 1, 3, 3, and 1. Okay, so we're okay so far with what we're doing here. Alright, if I just go over one last one, just to sort of finish off, n equals 4. So that would take a lot of time to practice and get that multiplied out, but eventually what that would lead to is x to the power 4 plus 4x cubed y plus 6 lots of x squared y squared plus 4 lots of xy cubed plus 1 lot of y to the power 4. Okay, and again, if we recorded just the coefficients in front of each term, we would get a 1, 4, 6, 4, 1. Okay, and so on. Okay, now how I've actually laid out my answers here, you can see there's a triangle forming, isn't there? Okay, that's actually what's known as Pascal's triangle. Okay, and these numbers are not by accident. Okay, now I know we've got them from the coefficients here. Okay, but they're not by accident that these numbers match these numbers and then vice versa, which you'll see later on. Okay, so that creates what's known as Pascal's triangle. So let's actually formally write what that is. So Pascal's triangle we talk about the rows, okay? So in row 0, that was when n was 0, okay? We had one term, which was 1, so we noted that as a 1, okay? If I go to row 1, then it was a 1 and a 1 that we had. If I go to row 2, then it was a 1, 2, and a 1. Row 3 was 1, 3, 3, 1. Row 4, 1, 4, 6, 4, and 1. Okay, so that's as far as we took it. We took it to the 4th row. Okay. If you actually might be able to spot what's going on here. Yeah, every time we start a row and finish a row, we end up with 1. Yeah, that always happens. So let's say if I wanted to think about what the 5th row would look like. Okay, now I haven't multiplied this out, so I can't use my coefficients up here, but this is how you actually work out what the constants or the coefficients would be. It would start off with a 1. Then what you do is, to get the next one, you add the 2 numbers above it. So for example here, if you look at this 2, the 2 numbers above it were a 1 and a 1. 1 and 1 gives you 2. Yeah? If I then go to say, let's highlight this 3, yeah? To find that 3, I would have added the 1 and the 2 together. Yeah? Same with this 3 over here, I'd add those 2 and that one there, that would give me 3 there. Okay? So the numbers above it add to give you what the number below would be. So if I go to what row 5 would be, so the number in between 1 and 4 would be a 5. The number between 4 and 6 would be a 10. 6 and 4 would be 10. 4 and 1 would be 5. And I know that this row finishes off with a 1. So I've actually managed to work that out without actually expanding all x plus y at the power 5. Okay? And that pattern works throughout all the rows here. So if I go to row 6, okay, start with a 1. 1 and 5 would be 6. 5 and 10 would be 15. 10 and 10 would be 20. 10 plus 5 would be 15. And 5 plus 1 would be 6. And I'd finish off with a 1. Okay, so they'd be all the constants that I would get if I multiplied out a bracket in the form x plus y to the power 6. Okay, and you can see this goes on and on. Yeah, you can see this goes on and on. So what that means is if I was to multiply out something like x plus y to the power 5, which is what we didn't do that one. Oh, sorry, not x plus y 5, sorry. Let's change that a bit. Let's change it to x plus 3 to the power 5. Oh, no. Sorry, man. Sorry. Try that again. Got my numbers wrong way round. X plus 5 to the power 3. Okay? So that means I'm thinking about, because my power's 3, I'm thinking about the 3rd row. Okay? Therefore, these terms are going to be, these constants are going to be in front of each thing. So how that would multiply out would be, if I look at the first number in row 3, it's a 1, so it's going to be 1 lot of x cubed. Okay? My next number is 3, so it's going to be plus 3 lots of, it's going to be x squared, so the x's go down in power. And then we multiply it by the other term, which is a positive 5. Okay? So I'm just using the 3rd row here. If I then go to what my other number after the 3 would be, it's another 3, so that's going to start me off. So the next x power would be an x to the power 1, which is just an x. Then the 5 would go squared. The 5 is going to go up in power. And then, last but not least, I'm going to have 1 at the end of row 3, multiplied by, no x's left because x power 0 is 1. It would be multiplied by 5 cubed. Okay, so the powers of the first term's going down as we go along the row. The last part of the bracket, the powers go up. Okay, you can see how the 5, the power goes up with the 5s as we go along. And if I tidied that up, I would get x cubed 3 times 5 is 15, so that's going to be 15x squared. Okay. 5 squared is 25, multiplied by the 3, it's going to be 75 lots of x. And 5 cubed would just be 125 there. So that's me actually managed to multiply out x plus 5 to the power 3 without actually breaking brackets. I've just used Pascal's triangles rule to do so. Okay, we okay with that so far? Okay, that is what's known as the binomial theorem. Okay, but we're going to expand on that a bit more. What I'm also going to show you is how Pascal's triangle can also be written in terms of binomial coefficients, which we've seen in the last video. Okay, so if we go comparison of Pascal's triangle with binomial coefficients. Okay. So if you remembered when I said at the start, even though I showed you where the constants came from, the numbers were not a fluke. Okay, they definitely were not a fluke. Those numbers are always going to be the numbers we use in Pascal's triangle. Okay, this is the reason why. So if I think about row 0 again, okay, and if I think about what that means in terms of selected numbers here, if I've got 0 objects, then the only thing I can do is choose 0 of them. Yeah, I can't choose any more than that. Now, 0 choose 0, that is actually number 1. Okay, if you do that in a calculator, you'll get 1 as your answer there. Because there's one way to choose 0 things out of 0 objects, okay? You just don't choose any. That is the one way to do it, that's why it's a 1 there. Okay, if I go to row 1, so if I've got one object, then what I can do is I can either not choose any of it, yeah, don't choose that one object, so 1 choose 0, or I could choose one object, 1 choose 1. And that would be the values 1 and 1. There's only one way I could choose nothing of it, and there's only one way I could choose that one thing. If I then go to row 2, so I could have 2 objects if I choose 0, or I could have 2 objects and I choose 1, or I could have 2 objects and I choose both of them. Okay, and how many ways could I do that? Well, if I've got 2 objects and I don't want to choose any of them, well, there's only one way I can do that, and that's why each row starts off with a 1. If I've got 2 objects and I only want to select one, how many ways could I do that? Well, I've got a choice of which one I select, so therefore I've actually got 2 possibilities which one I choose. And that's why we get a 2 there. And then the last time, we know we finish off with 1 like that. So you can see that your binomial coefficients, it is the exact same thing as Pascal's triangle. Yeah, these coefficients that you get here are the matching coefficients you get in Pascal's triangle, which means that when you multiply out brackets, each term that you get in your final answer has a binomial coefficient attached to it. Yeah, as you've seen when we multiplied out brackets, it was the same numbers that we used in our rows to get the answer. Okay, so that's the comparison with it. Okay, so as these are the same, what that means for us is that we can use binomial coefficients to expand a bracket of the form x plus y to the power n. Okay, so we can use these coefficients, we can use the rows in Pascal's triangle rather than actually having to multiply out lots of brackets. Okay, so for example, if the power was to the power 10, I would just use the 10th row in Pascal's triangle as opposed to trying to multiply out 10 lots of brackets. Okay, it'd be a lot quicker that way. So, the binomial theorem, how it works is, Okay, so it's a very important theorem for this year. If I've got a bracket x plus y to the power n, then the power tells me which row I'm using. So the answers will look like, well, the first one you do is you choose 0, n choose 0, but your first term goes to the power n, yeah, the power that's on that bracket. Then we go to our second binomial coefficient for that row, so n choose 1. What we do is the x then goes down 1 power, so I take 1 off the power, but then my y, or my other term in the bracket comes in, okay, y to the power 1. Then got a second number in the row, n choose 2. Then again the x goes down 1 power, so it's going to be n minus 2. But my y goes up 1 power, so then it becomes squared. Okay, so you see how there's a bit of a pattern emerging here. One thing's getting decreased in power, the other thing's going up in power as it goes. Okay, and this happens in general. Okay, until you get to, say, an r term. Okay, so r is just a general term in that row. Okay, it could be 5, could be 12, whatever it may be. Then you have x x to the power n minus r. Okay, we went down r times from there, and then y is up at power r. Okay, and again that will go on and on and on until we get to the last term. So the last term is going to be n choose n, the very final one. There'll be no x's left at this point, and the only term we'd have left is the final term, but that'd be up at its fullest power, which would be n. Okay, that's what's going to happen when we multiply out the binomial theorem. Okay, you do one bit at a time, and there's just a pattern of what decreases. Okay, so your coefficients go along the row. Your first term starts off with the biggest power and decreases one at a time, and your last term gets introduced, and then it goes up in power one at a time. Okay, till the very end. And you can see there's a bit of a symmetrical pattern to this. Yeah. What's known as the general term. Okay, so in general, so how you write just the general term of this, it's n choose r x to the power n minus r y to the r, which is what I've got in my sequence. Okay, so if we know the value of n, which was the power we were given to start with, and I know which one I'm trying to find, which term, okay, which the r would help me, then I could find out in general what that would look like using that there. Okay, if I now look at that and I go into the formula sheet, so the formula sheet for the binomial theorem says this. Where am I? Yep. So if I've got a plus b, so again just two terms to the power n, then they use this sigma notation, starting off with, nope, not n equals 0, my apologies. Just n on the top, r equals 0, so r is always 0 to start off with. N choose r, a, n minus r, b to the power r there. Okay, so that's what it says on the formula sheet. Okay. With that bit there, just on its own, so without the summation sign next to it, that was the general term. Okay, just to find one general term. Okay, what we're doing is this sigma means that we're going to run through, starting off with r equals 0, all the way up to the final power n. Okay, so it could be 4, for example. So you start with 0, then you do it for 0, 1, 2, 3, 4, for example, to get all your terms. Okay, you put it into each bit here to find your terms. Okay, so that's how we're going to use this equation here, okay? Remembering, okay, and the bit on the formula also tells you that where inches are, okay, which can also be written as N capital C R, that would equal, if we use the rule from last lesson, N factorial, R factorial, N minus R factorial. Okay, so that's what it is. If we're allowed a calculator though, we can just use the choose button to get the value here. Okay, but if we don't have a calculator, we'd have to use this formula in order to get the values for here if we couldn't remember it from the rules. Okay, so that is what the theorem does. The theorem's going to expand brackets to any power for us. Okay, and we're not going to be talking about brackets at that point. We're going to just be using the coefficients to do so. All right, so let's look at an example. Okay, so let's say I wanted to go with the example x plus y to the power 6. Okay, so using the formula sheet, okay, then I know here that n is 6 and r starts off to be 0, but then it goes all the way up to 6. Okay, I'm going to have to do it for all 7 terms in total if you include the 0. Okay, so if I expand that, so I just take one of these at a time. So let's make r equals 0 to start off with. That's going to be 6 choose 0. Okay, a is my first term, so it's going to be an x. Okay, n is 6. 6 take away 0 is going to be x to the power 6. Multiplied by y to the power, or r0, so that's just 1, so it just leaves me with that there. So that's my first term in there. My second term, so when r is 1, so it's going to be 6 choose 1. Then it's going to be x to the power 5. We take 1 off the power that it started off with. And then it'll be y to the power r. R is 1, so y to the power 1 is just y. Okay. Plus 6 choose 2, x to the power 4, y squared. Okay. Plus 6 choose 3, x cubed, y cubed. Plus 6 choose 4, x squared, y to the power 4. Plus 6 choose 5, x to the power 1, y to the power 5. Plus 6, choose 6. No x's left because it's a power 1, it's a power 0, which means it's 1, y to the power 6. Okay, so I did not have to break brackets at all with that. I just used the theorem to write down each general rule, and I'm summing it up, I'm adding it up as I go along. Okay, so the only thing I need to do now, just lost my numbers here, is write down what the coefficients are attached to these things. 6 choose 0, well, that's the start of our row. The start of our row is always 1, so it's going to be 1 lot of x to the power 6. 6 choose 1, that's going to be 6 x to the power 5 y. Plus 6 choose 2, which should give you the answer 15. You can check that in a calculator as well. X to the power 4 y squared plus 20 x cubed y cubed plus 15 x squared y to the power 4 plus 6 lots of x y to the power 5 plus 6 through 6 is 1 y to the power 6. Okay, so you can see, and if you actually check back in Pascal's triangle, we wrote down row 6, those were the constants that were in row 6. 1, 6, 15, 20, 15, 6, and 1. And you can see there's a symmetrical part with the coefficients too. Yeah, that was one of the rules that we actually wrote down last week as well. Okay, so for example, n choose r is the same as n choose n minus r. Different side of the row basically. Okay, so that's an example there. We'll look at a second example just to show you that it's not, you do, the constants do change, but only if there's only if the brackets are more complicated inside. Okay, so for example 3, let's go for a 3a plus 2b to the power 4. Okay, so again, maybe worth writing the date here. So n is my power, so n's only going to be 4 this time. R starts off at 0, but we need to take it all the way up to when r equals 4. Okay. It's too late then. Time to hair's got. That was worth it. Right, we'll have to go and edit this now. Right, okay, so let's start off with my theorem. So I'm starting off when n is 4, r is 0, but this time my first term is 3a, my second term is positive 2b, okay? So you'll see how we have to deal with that. So start off 4 choose 0, okay? Then we take the first term, which is going to be 3a to the power 4. Then it's going to be 4 choose 1. Then it's going to be 3a to the power 3. With my second term, 2b, multiply that to the power 1. Then it's going to be 4 choose 2, which is going to be 3a squared, multiplying 2b squared, plus 4 choose 3, 3a cubed, not cubed, sorry, power 1, 2b cubed, plus 4 choose 4, and then the only thing I have left will be 2b to the power 4. Okay, so we just use that rule to expand everything there. Okay, at this point, it's probably worth still having everything separate just now. Okay, so 4 choose 0 is 1. Therefore, that's just a 1 there. 3 to the power 4. 3 to the power 4 is 81. So the first term is going to be 81 a to the power 4. Then 4 choose 1, well, that's going to be 4 multiplied. I've got 3 cubed, that's going to be 27. But I've also got to multiply that by a 2. So I've got 4 times 27 times 2 there. Then I'm going to have a cubed b. Okay. Then 4 choose 2, that is 6. And then I'm going to have multiplied that by 3 squared. 3 squared is 9. Multiplied by 2 squared, which is 4. Then I'm going to have a squared b squared. Plus 4 choose 3, that's going to be 4. 3 on its to the power 1 is just times by 3. 2 cubed times by 8, that's going to be attached to an a b cubed. Plus 4 choose 4, that's just 1. 2 to the power 4, which is 16. 16 b to the power 4. Okay, so you just got to be careful that you've got to remember your powers on your constant, your numbers inside the brackets as well, okay? So if I tidy that up, I'm going to get 81 a to the power 4. My next term becomes 216 a cubed b. Third term becomes 216 a squared b squared. 4 times 3 times 8 will give me plus 96 ab cubed. Then I had plus 16 b to the power 4. Okay, so you can see we just had to be careful with our powers there. Alright, Okay, that will do us for today.